This lesson is about geometric series. You've already studied what a geometric pattern is. I want you to recall that a series is a sum, first of all, so we're going to be adding up terms, and also that a geometric pattern has a common ratio r, and it's defined in this way, that any term divided by the previous term gives that value r. That's why it's a ratio, and it's in common. Also, we've learned before that any term in a geometric pattern can be described based on the first term multiplied by a common ratio n minus 1 times in the exponent when you have a geometric sequence. We can write a geometric series this way. The sum of n terms is based on the first term, second term, third term, and so on all the way to the nth term, using the geometric pattern of multiplication by common ratios. Now, if we take that same pattern, which I'm going to call equation 1, and we multiply by negative r, we get negative r times the sum equals a times negative r, which is negative ar, and so on, a progression of terms. And you notice that these are shifted from the first series. That's by design. I'm going to call this the second equation. Now, if I take equation 1 and subtract equation 2, I would get this. The sum of n terms minus r times the sum of n terms equals a plus ar minus ar, then ar squared minus ar squared, and you can start to see why I formed it the way that I did. That's going to continue like that all the way up to ar exponent n minus 1 minus ar exponent n minus 1, and lastly minus ar to the n. This term is on its own. I can factor s sub n out of this, leaving 1 minus r. I will get a plus 0 plus 0 plus 0 all the way through this progression minus ar to the n. Now if I isolate for s sub n, I get a minus ar exponent n all over 1 minus r, or more commonly it's written as s sub n equals a bracket 1 minus the common ratio to the nth power over 1 minus r. This is the formula for a geometric sequence's sum. It relates 1, 2, 3, 4 terms are related. Maybe I should say 4 variables are related. So 3 of them would need to be given to you to solve for a fourth. Let's work with some examples. First up, let's find the sum of 9 terms given the first term and a common ratio. So the fact that we said 9 terms implies n equals 9, so we're given 1, 2, 3 things. We want the sum of 9 terms. That's going to be based on the first term, bracket 1 minus common ratio, exponent of n, over 1 minus common ratio. Alright, simplifying a little bit, I can bring that bracket out for the 2 because it's a positive number, it doesn't impact anything. The denominator is negative 1. So I have a negative divided by a negative and the number's 1. I could just rewrite this as 6 times the sum of 1 minus 2 to the 9. And if we get a calculator, let me reach for one here. 6 times 1 minus 2 exponent 9. Check my work to make sure that I did it right. I get negative 3066 as my sum. Now remember, we are growing because the common ratio is 2, so the numbers are getting larger, and a was negative, therefore every number in this particular series is negative and growing. So a negative large numbered sum shouldn't be a surprise. Let's look at the next question here. Now I have 10 terms. A is 3 halves, r is negative 1 half. Again, n equals 10, so I'm given the same information. I want the sum of 10 terms. I put my first value here, 1 minus, and I'm going to put a bracket there for the negative 1 half, exponent 10, 1 minus bracket negative 1 half. Now be careful with the signs here because I'm subtracting negatives. I have 3 halves, 1. Now a negative number raised to a positive exponent is going to be equivalent to a positive number, so I can remove that negative. The denominator, subtracting a negative, is like adding. 1 and 1 half is 3 halves. Notice how I have the common factor of 3 halves. So this is going to be 1 minus 1/2 exponent 10. And again, we're going to use a calculator to find out what that is. And I get decimal 99902 rounded off after several decimal places. Okay, here's another example now. I want to talk about sigma a little bit. We've already talked about sigma in a previous lesson. And I want to go back and do sigma again here. I have two sigma patterns that I'd like you to pause and expand and then look for the sum. Okay, I'm assuming you've already tried that. This has a counter variable of k, and I see that I made a typo here. This should be k as well, if that's going to be k. That might have confused you, sorry about that. 2 bracket 1 gets substituted first, plus 2 bracket 2 minus 4 gets substituted next, and so on. And the last term will be 2 times 10 minus 4. Now I skipped the middle terms. There are going to be 10 terms here. When I start from 1, end at 10. Let's expand. 2 minus 4 is negative 2. 4 minus 4 is 0. The next term, I probably should have written it, 2 times 3 minus 4 is positive 2, and so on, and I end with 20 minus 4, or 16. Now, looking at this pattern, we can see that we're actually increasing by 2 every time. This is arithmetic. So to find the result, if I wanted to actually find the sum, it's like summing 10 terms based on the first term of negative 2, the last term of 16, divide by 2, multiplied by the number of terms. We did that in a previous lesson. That's 14 over 2, which is 7 times 10. 70 is that sum. Let's look over here. Okay, now in this one I have a bit of a different pattern here. I have 3 with an exponent of j, the variable here, with starting at negative 1 on a base of 1/2. So that's going to be negative 2. The next term is going to have a 0 substituted, minus 1, so that's a negative 1, and so on, ending at 3 exponent 1/2 with a 4 substituted, minus 1, or 3. Now, a negative exponent means reciprocal, so 1/2's reciprocal is 2. 2 gets squared, making 4, so this is 12. 1/2 to the negative 1 is like 2. This is 6. I'm going to proceed like that, and we're going to end with 3/8. This is geometric. Now, I did this on purpose. I wanted to show you and remind you that sigma notations do mean sum or series, but they can be any type of series. They can be arithmetic, they can be geometric, or something else. In this case, I'm summing from negative 1 to 4, so 4 take away negative 1 is 5, add 1 is 6. There are actually 6 terms there. You may want to pause and think about that. First term, 1 minus the common ratio, moving from 12 to 6 and so on, is 1/2. The exponent is 6. 1 minus 1/2. All right. 1 minus 1/2 is half. Dividing by half is like multiplying by 2. So I can change that to 24 bracket 1 minus 1/2 exponent 6. And I'm going to use my calculator to find that result. And I get 23.625. All right, now notice, I wanted you to be aware of something here. In the arithmetic sequence, my common difference was 2. Notice the 2 multiplier on that counter variable. In the geometric, my common ratio was a half. Notice the 1/2. There's some patterns that you can read and interpret in a sigma that tell you what's going on. This is an exponential type of function in part B. Part A is a linear function. Linear functions make arithmetic. Exponential, or power sort of a relationship, makes a geometric situation. One more example for you here. Write this sum 8, 4, 2, and so on, ending at 1 over 1024, using sigma notation. All right, what we want to recognize here first up is that this is a geometric pattern, and it has an a value of 8, and it has a common ratio of 2. We also need to figure out how many terms we have. We need n. So I will write t sub n equals ar exponent n minus 1. Let's put the last number in for t sub n, put in a, put in r, and we're going to solve for n. All right, so 1024, we should try to figure out what this number is using a base of 2. And if we do a little bit of experimentation, we will find that it is exponent 10. This is 1 over 2 to the 10. Now 8 is 2 cubed. Okay, and 2 cubed could be written as a part of this power over here, so 1 over 2 to the, mistake, 1 over 2 to the exponent 13 equals 1 over 2 exponent n minus 1. Now, I'm going to rewrite this. 1 over 2 to the 13 could be written equivalently as 1 over 2 to the 13. I can now equate the exponents, getting n has to be 14. There are 14 terms in that geometric sequence. So, lastly, let's write a sigma. I'm going to say k equals 1. We often start at 1. I want 14 terms, so I stop at 14. And let me put my a value here. Let me put my r value here. And all I need now is to figure out what to do with k with this counter to make the exponent that I want. Now on term 1, I want it just to be 8. So I don't want this exponent to have any value other than 1. The way to do that is to make this exponent 0, so that the power, rather, is 1. So let's say k minus 1, and let's check. Substitution of 1 here makes an exponent of 0. That's going to give me a power that's equivalent to 1. 1 times 8 gives me the first term. I know I've got 14 terms. I know I've got my common ratio. So this is a pattern that will work. It's not the only one. I could do some other things like starting at 0, ending at 13, and I would adjust my exponent. Let me show you what that looks like. 0 to 13. Now I would have just plain k. Again, because the substitution of 0 gives me the first exponent that I want, leading to a power of 1. I could also absorb the 8 with the 1/2, recognizing this as 2 cubed, and put it into here and adjust the exponent. I'll leave that with you as something to try out. That's the basics of what's going on with geometric series.